Assalamualaikum and good afternoon, everyone.
Waalaikumsalam, Doktor.
Waalaikumsalam, Chef.
Okay, so before we continue on last week lectures on Hurwitz criteria, so let's revise or recap on what we have learned last week. Okay. So last week we have learned about Hurwitz criteria, how to generate the Hurwitz table, and then how to interpret the table to find or to determine the stability of a transfer function. And we also have done tutorials, part of the tutorials, question 1A and question number 2, the first block. So today let's do question number 2, second block diagram. And then we will continue with the lectures. Okay, so on the second block diagram, so there are two blocks that are arranged in cascade. Okay, so the controller and rubber actuator and load are arranged in cascade. So before you can do the route table, what you need to do is you need to simplify the block diagram first to get the closed loop transfer function. Okay, so let's simplify this block diagram and try to obtain the closed loop transfer function. Okay, so the block is arranged in cascade. Okay, so we get just basically multiply the controller, the transfer function of controller, and the transfer function of the rubber actuator and load. And then all of these are in feedback with the unity. Okay, so it's a unity feedback. So cascade plus unity feedback. Okay, so our closed loop transfer function equals, so we can use the formula for feedback. Okay, so since this is negative, so you use plus. Okay, so our G is just cascade, so we get K times S plus 1 times S plus 10 divided by S plus 5 times S squared plus 0.6S plus 9, and then divided by 1 plus, so same thing here, okay, so H is 1. Now we can simplify this to get a single numerator divided by denominator. So we get okay. So we take the denominator and then we generate the Hurwitz table. So the denominator. So we expand this. So we get s power of 3 plus 0.6 s squared plus 9s plus 5s squared plus 3s plus 45, and then plus expand this one. So we get k s squared plus 11k s plus 10k, and then rearrange in terms of order, okay? Power of 3, power of 2, and so on. So 5 plus 0.6. So you get 5.6 plus k. Then 9 plus 3, 12 plus 11k. Then plus 45 plus 10k. Now you can use this denominator to form your to generate the route table. So we start with s cubed followed by s squared. Then you fill the two top rows using the coefficient, and then fill it alternatingly. Okay, so we start with 1, and then 5.6 plus k, and then we have 12 plus 11k, and then we have 45 plus 10k, and then we find the s1, the row s1 using the determinant. So it's the determinant of negative determinant of 1, 5.6 plus k, 12 plus 11k, 45 plus 10k. Okay, so divided by 5.6 plus k. Okay, so let's say this is A, okay. And we have 0 here. And then for S naught, so it's just this one, 45 plus 10k, and 0. Then to find the range of k for stable system, then you need to check for the first row. So in the first row, all of the values in the first column. So all the values in the first column must be positive, or there is no sign changes. Okay, there are no sign changes in each of the row in the first column. Okay, so we start with s squared. Okay, so in s squared, 5.6 plus k must be positive. Okay, so 5.6 plus k must be positive for stable system. So we have k bigger than 5.6 negative. Okay, so that's the first k. And then we look at S naught. So we have 45 plus 10k must be positive. So we have k bigger than negative 4.5. Okay, now we look at s power of 1. So s power of 1. So we need to simplify this. So we have so this must be positive as well. So simplify. So we get, so this can be expanded. So kena guna calculator lah. We have 7.2 plus okay, so we simplify this further. So we get 11k squared plus 63.6k plus 22.2. So we get a quadratic equation. So we need to find the value of k. So use quadratic equation formula. So we have k as 0.373 k plus 5.409. Okay, so to find this range, then you need to use what you have learned in maths. Okay, form 4. So tiga desain. So kes satu lengkungan kuadratik. So we have 0.373. Oh, sorry. So we have negative 5.409 here and 0.373 here. So we want this to be bigger than 0. So we take the above one. So the range is should be k less than negative 5.409 or k bigger than negative 0.373. Okay, so let's take all the values of k. So we have 4 different range of k. Now we need to combine all the range into a single range for range of k for stable system. So what you need to do is you need to draw a number line. So first we have 5.6. So we have negative 5.6, and the k is bigger than negative 5.6. Then we have negative 5.4, maybe here, negative 5.4. And then K bigger than negative 0.37. So the range is less than negative 5.4 and bigger than 0.373. And then we have the last one, negative 4.5. And it's also bigger. Macam salah tahu kenapa. Okay, whatever. And then from this three different range, K bigger than negative 5.6, K bigger than negative 4.5, and these two range here, we need to find the location of the number line here that crosses or intersect all of the lines. Okay, so if you if you take this range, then it only intersect two lines. If you take this range, only one line here. If you take this range, then only two lines. So you need to take the last range here because it intersect all of the lines. So the range of K for stable system is when K bigger than negative 0.373. Okay, so the other range are not accepted, okay? Not causing system to be stable. Only K bigger than negative 0.373 will make the system stable. Okay, any question before we proceed?
Sure. Yang ni kalau semuanya stable kan?
Ya, betul.
Kalau tak stable, cara yang sama ke lain?
Kalau tak stable, jaranglah dia nak tanya kalau tak stable. Selalunya kalau tak stable, one of the values in this column will be negative. So selalunya kita berminat dengan sistem yang stable. So dia tak tanyalah yang tak stable. Mungkin dalam benda lain kot.
Okay, sir.
Okay, now let's continue with our lecture from last week. Okay, so last week we have learned about the how to generate and interpret Hurwitz method for normal case. And we also have special cases that requires you to modify the method on generating the Hurwitz table. So there are two special cases. So the first case is when you encounter a zero in the first column. So when you calculate your Hurwitz table or the determinant, you will get a zero in the first column, only in the first column. So when you have zero in the first column, then you need to modify your method. And then another case is when you encountered a row or entire row consists of zeros only, or zero, value zero. So you need also need to modify the method. Okay, so let's look at the case number one, when you encountered a zero in the first column. So let's say you are given this transfer function. So you generate the route table starting with s power of 5 and then followed by s power of 4, and then you fill the two top rows alternatingly with the coefficients. And then when you calculate for S3, you get a 0 here. So this is the 0. So when you get this 0, you need to do something. Okay, you need to modify your steps before you can proceed with calculating the subsequent rows for the next rows. So here what the method did was it modify the value 0 here by replacing this 0 with a small number, with a very, very small number represented by this symbol epsilon. Okay, so you replace the 0 with an epsilon, and then you continue the calculation as usual. Okay, because if you use this 0, then you cannot divide by 0 here. You get infinity. So that's why it replaced with an epsilon. Okay, so when it replaced by an epsilon, then you can continue as usual. Now your first row here will have this symbol epsilon. So after that, to interpret the table, what you need to do is you need to assume what happens if the epsilon is a positive values. So let's say a very positive, a positive small number, let's say 0.1. So you replace 0.1 in this epsilon. Okay, so you get first row as power 5, the value is positive. As power 4 is also positive. So when epsilon is a positive small number, so you get positive. And then you replace 0.1 in this second row, the row as power of 2. So you get a negative. Okay, repeat the process for S1. Replace epsilon with 0.1. You get positive and then positive. So here we have sign changes in the in positive epsilon. So we have two sign changes. Okay. And then you repeat the process by replacing epsilon with a very small negative number. So let's say we use negative 0.1. Okay, you repeat the process, same thing. So here we also have two sign changes. Okay, so since both of the positive epsilon and negative epsilon produce two sign changes, so you will have two poles that are located on the right half plane on the S plane, and this means that the system is unstable. Okay, so that's the method for that you need to do when you encounter 0 in the first column. Okay, so you replace 0 with an epsilon. Sometimes you find this method quite confusing, or maybe it takes a lot of effort, okay, because you need to assume epsilon positive and epsilon negative. So we have an alternative method to overcome the problem of the first method. So the method here is called reverse the coefficient of the denominator. Okay, so once you know that this denominator produce a 0, like this one produce a 0, so you can reverse the coefficients. Okay, so you reverse this coefficient by making it 3 s power 5, 5 s power 4, 6 s power 3, 3 s power 2, 2 s plus 1. Okay, so you just reverse the coefficient. And then once we reverse, then you can use these new polynomials into to generate the Routh table. Okay, same procedure to generate the Routh table. And then you look at the first column. Okay, so in the first column, you have two sign changes from here to here, and then from here to here. So you will produce the same results as using the first method. Okay, so there are two sign changes, meaning that there are two poles on the right hand plane on the S plane, and the system is also unstable. Okay. Any question before we proceed? Okay. Now we look at case number 2, when you encounter 0 in an entire row. So let's say you are given this transfer function, and then you generate the route table. So start with S power 5 and S power 4, and then fill the two top rows alternatingly with the coefficients. And then you calculate S power of 3, the row S power of 3, using determinant. So when you calculate S power of 3, what you get is all values are 0 in that row. So now we need to do something, because if you continue with this 0, you will get infinity for the subsequent rows. So what you need to do in this case is you need to use the row above of the row that contains zeros. So use the row above to generate a polynomial. So in this case, we use row S power of 4 to generate this polynomial. Okay, so we use 1 S power of 4 plus 6 S squared plus 8. Okay, start with S power of 4 and then you reduce by 2. Okay, and then after you generate this new polynomial, you differentiate this polynomial with respect to S. So you get 4S cubed plus 12S. And then we can use this new differentiated polynomial to replace our row number 3, S3. So we use 4 and 12 and 0 instead of this value here. So we use this new value. Okay. Then using the new value, we continue with the calculation of the subsequent rows. Okay, S squared, S1, and S0. And then we can analyze this by looking at the first column. So in the first column, there are no sign changes, meaning that the system is stable. Okay, another example. So let's say you have this polynomials. So you want to determine how many poles are on the right hand side and left hand side. So you generate the table starting with S power of 8 and then S power of 7, and then continue the calculation. And then here, when you get S power of 3, you get all values are zeros for the entire row. So what you need to do is you look at the row above, row S power 4. So we have 1 here. So it becomes S power 4 plus 3S squared plus 2. And then differentiate these polynomials. So you get 4S squared, 4S cubed plus 6S. And then use these values to replace the row S3. And then from the new values, you continue the calculation for row S2, S1, and S0. Okay. So for the first half of the table, there are two sign changes from here, S7 to S6, and from S6 to S5. Okay, so meaning that there are two poles on the right hand side of the S-plane. And then the second half of the polynomials, there are no sign changes. Okay, no sign changes here, meaning that there are no poles from second half. They are located on the right hand side of the S-plane. Okay, so this is because of the symmetry. So this is you can ignore the symmetry thing because this more towards theoretical mathematics. Okay. So here the important thing is that there are two sign changes generated from the table, meaning that there are two poles located on the right hand side of S-plane. Okay, so that's it for the two cases of special cases using Routh-Hurwitz criteria. So let's look at the tutorial. We have two more questions, okay? Okay, so we still have question number 1B and 1C. Okay, so let's look at 1B first. So we have GS equals, so 1000 divided by S power 5 plus 2S power 4, 3S cubed plus 6S squared plus 5S plus 3. Okay, so this is an open loop system, so you can use this transfer function. So we take the denominator, and we generate the Routh table. We start with S power 5 and then S power 4. So we get 1, 2, and 3, 6, and 5, and 3. And we can calculate for row S3. So we get 1, 2, 3, 6 over 2. So we get 0 here. Okay, and then the second column, get 1, 2, 5, 3. So 10 minus 3, 7 over 2. Okay, so we get 0 in this first column. So we need to modify the transfer function or modify the denominator according to case number 1. Okay, so we use the alternative method, which is by reversing the coefficient. So we reverse the coefficient. So let's say ds, we have 3s power 5 plus 5s power 4 plus 6s cubed plus 3s squared plus 2s plus 1. Okay, so we use this new polynomial to create or to generate the table. So we start with s power 5 and then S power of 4. So we have 3, 5, we have 6, 3, and 2, 1. So we calculate for row S3. We have so 9, 11, 30, 30 minus 9, 21. So 21 over 5. Okay, the second column. Ten minus 3, 7 over 5. Okay, so banyak sangat kita banyaknya. So we have 5, 3, we get 1, here, zero, over here we get 1. Okay, kira jap. So we get 4 over 3. So we have negative 7 over 4. Okay, nanti check balik. Tak tahu betul ke tak. And now we have two sign changes here. We get first sign changes from here to here, positive to negative, and then negative to positive. So from this route table, we know that there are two sign changes. So two sign changes mean that two poles on right hand side of S plane. So therefore the system is unstable. Okay. So when you encountered a 0 in the first column, then you reverse the coefficient. So now let's look at question C. So for question C, we have the denominator equals s power of 6 plus s power of 5 minus 2s power 4 minus 3s cubed minus 7s squared minus 4s minus 4. Okay, so we start with generating the table with s power of 6 and s power of 5. So we have 1, 1, -2, -3. -7, -4, -4, and 0. So we calculate row S4. So we get -1, 1, 3. 3 tolak 2. 1, -1. Okay. Okay, and then the second column. Right, tambah 7, 3, -3. Then we get -4. And then row S3, you get all zeros. And then from here, you need to look at the row above S3 to generate new polynomials. So we generate new polynomials from row S4. So we get S power of 4 minus 3 S power of 2 minus 4. And then differentiate. You get 4s cubed minus 6s. Then we use these new values to replace row S3. So you get 4 minus 6, 0. And then we continue the calculation for row S2. So start with row S4. So we have 1 minus 3, 4 minus 6 divided by 4. So you get minus 6 plus 12. So you get minus 6, 6 over 4, so 3 over 2. And then this one. So you get minus 4. And then continue for row S1. And then this one you get 0. This one you get minus 4. Okay, so after you generate this table, then you can calculate the sign changes. So calculate from determine from above. So this is positive, 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 and then this is positive, 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 and this is negative. So you have one sign changes here. Okay, so the system has one sign changes from the Routh table, meaning that there is one pole in right hand side of S plane, and the system is unstable. Okay, any question before we end this lecture?
Sir,
Yep.
yang untuk buat create equation baru tu memang start daripada S04 ke?
Yang ni ke? Dia kebetulan dia S04. Tapi banyak example memang start pada S04. Tapi mungkin ada case lain dia start dengan S06 ataupun S08. Rasanya dia akan nombor genap. Dia jarang S power 5 rasanya lah. Tapi examples macam dalam buku ke, kat internet ke, dia akan bagi memang S power of 4. But you need to look at when you have zeros in this row, for example row S3, then you need to look at row above of that zeros. So in this case, it's row S power of 4. Then you create or generate this new equation and then differentiate. So let's say this is row S5, for example, instead of row S3. So let's say you get row S5 here. So you need to look a row above, which is S6. So you will start with S power of 6 minus 3S power 4 minus 4S squared plus 0, something like that. Okay, so kena tengok row mana yang kosong, dan tengok row atas dia, and then baru create new equation.
Okay, faham saya.
Alright. Okay, any more question? Okay, so regarding this Hurwitz criteria, I want you to start understand how to generate the table and how to interpret the table. Okay, how to determine how many sign changes and so on. Because in the next lectures, lecture 4B, 4C, and then lecture chapter number 5, we are going to use Hurwitz criteria a lot. And maybe while using the Hurwitz criteria, I didn't explain from beginning, like start with S6, why start with S6, and then how to get the determinant and so on. Okay, because it will become a method that you need to understand already, or fully understand already. Okay, so I hope you guys can understand this from now, so that we can use it later in subsequent lectures. Okay, so that's it for today's lecture. Ada soalan? Okay.
Sir, nak tengok yang example 1B boleh?
So untuk 1B ni,
Yang bawah, yang dekat table yang bawah tu,
so
ada kosong-kosong tu, kira sir tak kira?
yang ni kosong sebab dia punya determinant 3500. So kosong lah. So yang ni kosong ni,
Tapi sepatutnya kena kira lah sir?
tak payah pun tak apa, sebab ini tengok tahu kosong macam tu.
Oh, tapi kalau kira macam yang sebelah tu pun memang akan dapat kosong lah sir.
Betul. Macam ini pun kosong sebab 5, yang ni kosong-kosong. Yang ni kosong sebab ni dengan ni darab kosong dengan kosong ni.
Okay.
Ah,
Point sir.
alright. Okay, any more question before we end this lecture?
No sir.
Okay, so if there is no more question, see you on Wednesday with new lecture 4B. And that's it lah. Okay. So Assalamualaikum and goodbye.
Thank you, sir.
Okay, thank you sir.